Hey, what's going on guys, Komiki here. In this video we're going to learn how to assemble move command from x86 assembly language, Intel syntax to x86 machine codes. And I'm going to be using NASM, which is the NetWise assembler, in order to verify whether I did this properly or not. And here we're going to be uncommenting command by command and then assembling to verify when we find this value by hands, just to verify. And that's pretty much all about it in regards to the way to go. So before we start, one more little thing. So when it comes to referencing variables, so in our case we have a variable called message and there is just a string there. So there is no such thing as variables in machine codes. In machine codes we deal with specific memory addresses. So just to give you an idea, so I just put some zeros after the instructions, and at the very end I have this kind of message variable, but well, call it variable, but again, like literally. So let me just assemble this file. So I can say nasm-f bin move.asm -o move, and if it assembles, I want to use hex editor xxd to open move, and this is pretty much all about it. So here we have the address of where the message locates. So starting from this, so this address points to the very first variable, to the very first letter within this string, and when we will want to deal with this variable, like you'll see this you'll now understand what I'm talking about. So what we literally gonna be dealing with is the exact address. Well, usually when you just write type code in assembly, you don't do things like this, and the message gets placed just right after the instruction, but it's not really that clear to see the addressing in that case. So I just use this fixed address for a variable, so it would always be the same for all the instructions. Okay, so I hope it's clear, because otherwise it would just the instructions themselves taking some place, and assembler would be recalculating the offset for the string variable, and we will need to do this to do the same. It's a little bit of a distracting thing, so we really want to focus on how to encode this assembly language mnemonics to opcodes, to operation codes, and followed by the operands according to this format. So here we have sorry. So here we have a formatting for a move command. So there might be different ways of how the move command might be defined. So for instance, we can deal with immediate data go into register. So in this case, we'll have this format. I will now talk through the elements. Then, for instance, register to register, and we have this format, and so on. So segment to register, register to segment, register to memory, immediate data to memory, AX register to memory, memory value to AX register to memory value, to value at memory, to value at memory. This is going to be a more precise way of saying this. Memory value to AX and memory value to register. Okay, so the general formatting is first we have the opcode. Then this W stands, so if the registers, or if the memory that we're dealing with is either 8-bit or 16-bit. So if it's 16-bit, we replace W with 1. If we deal with the 8-bit register or 8-bit, like a single byte in the memory, then we use 0 instead of W if needed, if necessarily. Then mod stands for mode. So we use only two modes here. So the first one is 1-1, which is 3 in decimal, right? And this is the mode when we deal like register to register operations, and 0-0 is when we do memory to register operations, but then the following constant here, 001, which is 6 in decimal, tells us that we're using the direct address. So here we see that 110 is the matter of the direct address when we deal with register or memory. So here we use registers, and here instead of the register we use just the constant, and which specifies that the address following after is the direct address. By saying direct address, I mean the offset from the beginning of the file, from the very first instruction, and right over to right over in here. And when it comes to like working in the real mode, in a 16-bit real mode, it's absolutely essential to move the data sector, the data segment pointing to this absolute kind of location that won't be 0000. It would be somewhere in memory, and then the direct address would start from where the DS is pointing to, and then adding this offset. So I hope this is clear. So in order to make it work in a particular sector, when you're running it, you really need to make sure to adjust the DS register appropriately. Okay, but this is more like about assembly on its own. It's not really much about encoding, so let's better stay focused on encoding. Okay, so another two important things. So it's the order of how the registers are being encoded. So in case if we are encoding register, if we want to put a register to the segment register, or vice versa. In this case, or vice versa here. In this case, segment register for some reason always goes first. I say for some reason and have a bit of a doubts, because this is what happens by fact, and this can be practically proved by comparing the values with the assembler. But I actually didn't find this in the documentation. But this works, and this is pretty enough for us. Okay, and then when it comes to when we move in register to register, in the syntax we have destination register first and then the source register. However, when we want to encode them, source register goes first, so BX would go first and then AX. So that's another thing to bear in mind, because otherwise it might get really confusing. Well, okay guys, so now we are ready to start the actual encoding. It would get, I promise that it would get more clear by the time that when we're doing this. So let's start with the very first one. So first I'll encode by hand, and then we will verify with NASM. So currently we don't have any instructions. Okay, so this is the case is known as immediate data to register. So message, like from the assembly language perspective, we might think that message is just a variable, right? So we want to assign, so what the variable literally is, it's the address in memory. So from the machine code's perspective, this is just the matter of putting the immediate data, which is the absolute kind of address, the offset, like, well, not absolute, sorry, it's relative from the data segment, yeah. So, but anyway, this is the immediate data that we want to initialize SI register with. In example, when we want to print string, we want to point SI there, and then we can use load single byte and so on, but let's not get distracted. So immediate data to register, and we need to find the corresponding line here in this table. So immediate data to register, and then we just grab this entire thing and paste it here. So what we have here, so first we need to replace W's. As far as SI is a 16-bit register, so you see like 16-bit registers, SI is 16-bit, so we want to replace W with 1. Then the register itself, so we need to replace the register with the code of SI, which can be taken from here, and this is 001. So instead we say 001. And then we need to encode the data, and the data is the actual address. So in order to get the address, we can go back to where address occurs, and this is the address. However, we can't use the address, so instead of data we do put the address. So this would be hexadecimal, but here is the deal. We can't do it this way because x86 architecture is little endian, which means that byte order is opposite to the big endian actually, and here we have the big endian. So in order to swap this, we need to say, so okay, I just spent some time to demonstrate. So let's say we have hexadecimal value of, I don't know, some random value like this. So if we split this value by, so let's say this is the big endian, okay? So let's say this is encoded in the big endian, okay? Byte order, okay? So we split the bytes by 1, so 2 digits represent a single byte. And if we want to transform this to the little endian, and this is absolutely essential, because yeah, so all we need to do, we need to reverse the order of bytes. So 7, so this would be hexadecimal, so 7b goes first, so 7b, then 54 goes next, then fa, okay, then 12. So in little endian we'll have this sort of a thing. So if we have just 2 values, then respectively we just say fa and 12, okay? But in our case we have 0, 1, E0, so in order to replace those, it's literally, it's literally enough to just swap these 2 bytes, and that's pretty much all about it. So take this and place it here. Okay, this is, and H stands for hexadecimal, because here we have the binary part and here is the hexadecimal. But just to align bytes properly, we need to have 4 bits in a row, and 4 bits in a row represent a single letter in hexadecimal. And now we need to convert this to hexadecimal. So all zeros is the value of 15, so this bit is worth 1, this is worth 2, this is worth 8, and this is worth sorry again, like 1, 2, 4, 8, okay? In case, but it's worth it only in case if the bit is equal to 1. If it's equal to 0, it's not worth anything. So we need to, so we have 1 plus 2, it's 3, plus 8, oh my god, 11, right? And 11 in hexadecimal would be B. So we can say B here. Also, we can use a calculator if we're not sure that how things are going. So calculator is also on the cards. Okay. So B, then if here would it be like 1, it would be F, because 15, but minus 1, this is going to be E, B, E, and then the address, so E001. And this is the encoding. This is how this instruction eventually in machine code is going to be encoded like this. Now to verify this, let's assemble the code. So see, like I've uncommented the very first one, and let's just run the code and see what happens. So we have this BEE001, okay, which is exactly what we want to have. All right. So this is the first instruction. So I hope it's clear, and now I hope it would go faster. So let's go and encode the second instruction. So move AX to BX. So this is the case where register to register needs to be moved. So just paste this in. AX and BX are both 16-bit, so W is replaced with 1. 11 is the mode. It stands for that there is no memory, no memory displacement. We're working with the registers. And now the order of the registers is very important. So here is the hint. So first we need to put the source register, and then we need to put the destination register. Okay. So the destination register is AX, and BX is the source register. So here we need to have the value of BX, which is 011, 011, BX 011, and here we need to have the value of AX, which is 000. Okay, now let's adjust the layout. So we have 4 bits in a chunk. Okay, and now we need to turn this into hexadecimal. So this is gonna be 8. This is gonna be 8. Okay, this is gonna be 8, this is gonna be 9, 8 plus 1, 9. This is gonna be, so 15 minus 4, oh my god, 11, right? No, hold on a sec. 15 minus 2, I'm sorry, 15 minus 2, 5 minus 2, 3, 13, 13, this is D, okay, and this is 8, again. So this assembly line would get encoded as 89D8. But let's figure out if this is really so. So we have 89D8 right after, okay, 89D8 after this one. So 89D8, so far so good, and let's go further on, okay. So now the next scenario we might have encountered, and this might be on the cards when you want to initialize the data segment, but first you need to get to initialize AX with CS, and the next step DS to AX. This is the pretty standard routine to initialize the data sector to fit where the instruction pointer is within the current code segment. Okay, so segment to register. And here it is, so we have segment to register, and this is the format of the instruction. So let's put it in, okay. And now the order, it's important that segment register always goes first. I don't know why, but this is just like by fact this is so. So first, the CS is the segment register, so let's find the code for CS. It's 001, so here we can say 001, and then AX is 000, so here we can say 000. Now let's adjust the layout, and eventually we have this sort of a value. So we have, for this we have 8. For this we have 8 plus 4, which is 12, which is C. Okay, this is also C. Okay, and this is 8. Okay, so 8C, C8. Let's have a look. And 8. No, start from here. So here is the instruction 8C, C8. This one is from the previous. So 898, 8C, C8. So this is what we got, okay. Now let's move further on. So now we need to do the opposite. So we need to put the register to the segment, and this is the scenario. So when the register goes to the segment, hold on a sec. Yeah, I'm just getting confused by the order, because in assembly we have the destination here, so to the segment. So this is the destination, and what to move. AX, this is the source. Yeah, it just gets confusing a little bit. Okay, so register to segment, and here is the format of the instruction that we have. Okay, so now again, like despite the fact that the order like the source and the destination has changed, still we do need to use the same order. So first goes first segment, and then the register, well, segment register, and then the general purpose register to be exact. So DS, where is the DS? So here is the DS 011. So here we can say 011, and AX is 000. So here we have 000. Okay, now let's adjust the layout, and eventually we'll come up with. So this is 8. This is E. Okay, it was already, this is D, okay, and this is 8, so yeah, D. So let's check this out. So this should get encoded, assembled as as 8ED8, so let's check that out. Okay, 8ED8, which is true, so far so good, and we're going further on. Now things are starting getting a little bit complicated, but not that much really. So register to memory. So now before we start, like what this means in assembly, this means that within so here instead of 68, which is the very first byte in the string hello, in this string, we want to replace this well, actually, no, to be yeah, exact, actually, this. So first two letters, so it's not hello, it's hand assembly. Okay, so these two letters would get replaced with whatever we have in the DX register. So DX is 16-bit, hence not 1 byte but 2 bytes or a word. So that's hence the operation size. Okay, so this instruction would result in replacing this value with somewhat a different value, whatever value we have in DX. Okay, so it's not the matter of just pointing register to some sort of memory like we did here, but actually to change the value at the memory. Okay, let's say register to memory value to be more precise. Okay, and here to memory value. Okay, sorry guys, sorry for being distracted, I just needed to feed my cat. Okay, so I hope it's clear, right? So we do initialize the value at the certain memory address by whatever we have in DX. So it's really important to understand what exactly is happening. And now the register to memory value, and here register to memory value. So this is the formatting that we need. Okay, so again, make sure, yeah, register to memory. All right, so DX is 16-bit, and we specify the size to replace, to put there is word, which is also 16-bit. So W is going to be equal to 1, because it equals to 1 if we're dealing with the 16 bits. And then the register we're going to be taking data from is DX. So DX is 010. So here we can say 010. Now this is a constant which tells us that we're looking for a direct address, and now we just need to replace this address with a value for a direct address, which we already have, which is this one. Okay, and put it in and hexadecimal. Now let's adjust the layout so to have 4 bits in a chunk. Okay, and let's convert this to the actual instruction. So we have 8, then 9, then 1, okay, then 6, and then E001. And this is going to be the value of how, and this is the code to encode this string from x86 assembly to x86 machine code. So let's check that out. Okay, so 8, 9, yeah, starting from here, 8, 9, here it is, 8916, 8916, E001, E001, which is true, which is exactly what we wanted to have. So far so good, so let's go further on. Now the next thing to consider, we want the immediate data, we want to put some immediate data, some constant, let's say to the byte of the memory. So in this case, here, we're not going to be replacing, initializing the entire word, but only the first byte. So that's important. And this is the value for ASCII character A in hexadecimal. So by this operation, we'll literally replace the H by the A. Okay. And the correspondence, so immediate data to memory. So here it is, immediate data to memory. And so this is probably one of the most sophisticated instructions, but it's really simple on the real deal. So as far as we're dealing with 8 bits, so it's not a 16-bit, it's just the 8-bit. So W is going to be equals a byte, so not a word, just a byte. So this is going to be 0, okay, because 16-bit 1, otherwise 0. And also if we deal with a word, again, like we deal, this would be 1, but the byte would be just 0. Okay, so then what? The address. So address is what we have is E001 hexadecimal. It's direct address. Okay, and the same thing here. So we had this. So yeah, let me just. Yeah, so the mode is we want to put. We're working with the memory, but we're looking for a direct address. So this is the code for a direct address, and instead of the register, we don't have anything because there is no register here. But also additionally, we have a data. Okay, the actual constant that we want to put into the memory. Okay, so now now let's put this to the reasonable layout. Okay, now instead of address we have this E001, and instead of the data we have 61, and we don't need to adjust the NDNS here because this is the only byte, this is the single byte. Okay, so now let's turn this into machine code. So 110 is C, 110 is 6, then 0, then 6, then E001, and 61 as the immediate value. So this instruction should gonna be encoded like this. Okay, now let's check this out with the NASM assembler, and yeah, exactly what we have. So this is it. So we have C6, 06, E0, C6, 06, E001, E00161, which is exactly what we're looking for. Great. Okay, so the next thing, we want to move AX to the whatever available at the register AX to the value at memory. And now you might be wondering, what's the difference? So why can't we use like register to memory, right? But for AX, we just have a short instruction, which is shorter compared to a register to memory. And if you want to put AX to memory, it's literally enough to say like this. Okay, so we just say, so AX is 16-bit and we're dealing with a word, hence W is going to be equal to 1, and then just the address, which is E001 hexadecimal. We always deal with the same address here. So 1010 is 10, so this is A3 E001, and this is the instruction to encode this assembly line. So let's check this out using NASM. Okay, so here we go, A3 E001, which it is. Perfect. Okay, now let's go to the the next one. So also we might have the case when we want to put the memory value to AX. So it's also a bit shorter compared to putting the memory to the register. So we had memory to the register. Yeah, memory to the register is the next one. Okay, I'm sorry. So yeah, so if we want to put memory value to AX, in this case, it just by the way, I could have specified word here, even though it assembles like without that, but it's assumed. But because AX is 16-bit, hence we take the word, exactly the word at the message, but it's better to make it explicit in assembly. Okay, so memory value to AX, so memory to AX, and this is very similar to the previous one. The opcode is just slightly different. So here we have one, here is 0. Copy and paste, and W is equal to 1 because, sorry guys, because we're dealing with the 16-bit values, and the address is going to be like previously E001. Okay, so let's see. So 1010 is 10, which is A, 001 is 1, and E001. So we expect to have this value to encode this assembly line. So let's check this out. Okay, and we have A1 E001. So here we had A3 and here we have A1. Okay, and the final instruction and the final format for today is if we want to put the memory value to the register, so not to AX but for whatever other register but AX. So memory value to register, this is the very last line here. So just grab it, okay, and paste it here. So BX is 16-bit. By the way, we can specify word here as well. So BX is 16-bit, so W is gonna be equal to 1. Now, instead of the register, we can use the value of BX. So the value of BX is 011, so 011. And we have a mode working with the memory. Here we have a code for a direct address, and we just replace the direct address with E001 hexadecimal. Okay, yeah, I forgot to put hexadecimal here. Okay, so let's adjust the layout. Okay, and let's encode. So we have 8. It's always hard to get this one. 15 minus 4, 11. 15 minus 4, 11. This should be B. Okay. 1 E, and then E001. So just to make sure that this is really B, we had this somewhere. Okay, guys, and just when you do this too much, you just get a little bit exhausted. So let's turn B into binary. Yeah, 0100. Yeah, this is it. So this is B. This is B. Okay, so yeah, and this is the code. So let's check out whether it's whether it is so or not. And it is so. We have 8B1, 8B1E, 8B1E, E001. And this is pretty much all about it, guys. So we've learned of how one can encode x86 assembly move instruction from x86 assembly Intel syntax to x86 machine codes. And this is pretty much it from my side, guys. So I hope you've learned something interesting out of this tutorial. And in the next videos, we're going to be covering some other instructions. It's not really trivial to come up with this formattings for all the possible combinations, and I'm taking this from many different sources, and eventually I've realized that instead of having like multiple windows being open, it's just better to bundle it all together tightly, so we have the only source of where to reference this kind of like instructions and register encoding. And for jump command, for conditional jumps, we'll have another table specifying some specific conditions for jumping. That's gonna be interesting as well. So I hope you learned again like something interesting. Thanks for watching. Until the next time, and take care.